watch this at the... So here we are again in our training. We're in our second session. What have we been doing? So again, just to remind everyone here, we have Matt Paul from my team. He runs the training in my team. So if you need any support, feel free to reach out to him in the participants. You can reach out to him directly too, or just in the chat, so we can all see what we're asking. And again, you have, there he is, there's Matt. Thanks, Matt. And we have issues to support you outside of class as well. So you should be able to, and I'll show you them again now, but you should be able to ask questions outside of class. And we had some really good questions last time in class. So this is our training. We're on rockefelleruniversity.github.io, and we have a new link here Matt put in. So we have our link to our YouTube channel. Great, so you can come and see how to get help here and watch. Here's Matt.
Hi.
Hi, Matt. So you can see him introduce you to the courses, and we have some videos of the rest of the team as well there. But here are all our slides. I'm going to update this for Matt's email in the future. Here are all our slides, and we actually came and we looked at the intro to the course, what we were expecting to do. And here we are in our first course. So just to reiterate, if you need help, right-click here, and it will take you to our issues page. Don't have any issues. Someone closed my terrible pretend issue last time. If you need to ask a question, just raise your new question title here. Question. Description here. You can log a question and just come back, have a look. We will answer this when we can. Okay, so that's how we get going. And then we had our material, which we can download here. So every course section will have its own material. We click that, it's going to download to our downloads. But we can just follow along the slides here if we want. Or we have our slides embedded in the pages here. It's a bit of a pain as you can't just Control F search for if you want to go back in the exercises. I think this is kind of frustrating. But we have a page here, which is all the course in one long page. So if you want to do Control F and just move up and down that way, maybe that's easier. We find it easier, maybe me, but I think Matt too, to kind of talk through the slides. Okay. So we can get going on today. So here are our slides. We covered some of the intro, and I'll run through quickly what we did last time, but just to reiterate on this important part here, setting the working directory, we have our studio. Hopefully I'm sharing my whole screen. I think I am. Let's have a look. You share. I'm already sharing my whole screen. So this is what our studio looks like. Actually, it looks a little different. We have our script. We can type stuff here. Here's our console. This is the actual R window. We have our history of stuff we've done, environment. And this is our working directory at the moment, but it's showing us all the files. One easy way for us to set the working directory is just to create a new project, existing directory here, because I've just downloaded this. And actually, I put it on my desktop. Here it is. And we go to our course, and if we go in there, we can press open, and it's going to create a project in that directory. Okay. So now if I type in get working directory, it should tell me I'm in that directory. Here it is. The other ways to set your working directory, really easy ways, in the top on Mac, but also in Windows, it will be in the top menu. We have session, and we can go set working directory. We can choose our project directory. We can choose any directory. We can navigate around our computer that way. As I show in the slides here, you can also use just set working directory. Okay. Type in the actual full path. I find it easier in our studio just to do it in the GUI often. So we covered the basic types of data last time in our session one, and just to introduce us or reintroduce us, we came first off across vectors. Makes it a little bigger. So the first basic data type we saw was vectors. A vector is just an array of numbers or characters or logicals, but it's a one-dimensional array, and it is ordered, so things come out in a certain order. We can assign this to a variable, and the variable can be a word as well as just a letter. I might try to think of a word beginning with X, but you know, xylophone I'm not going to spell. Let's go for zebra. We can assign values to variables such as X or zebra, and then we can use indexing to retrieve values from these. So if I want to get the first value, if I want to get the second value of zebra, the third, I can also replace values inside my vectors. These aren't what we call immutable, they can be changed. Now if I look at zebra, the third position I've updated. The next thing we saw was matrices. So we had our one-dimensional vectors like this, or we can create them slightly differently. Let's create them. Now zebra is our one-dimensional array, ordered. We saw that we can turn our vectors into matrices, and all we need to do is have a vector ready, such as 1 to 10, and we can use this matrix function, and it tells us what we need to do there on the screen, and we'll say ncol equals 2, nrow equals 5. Okay, and by default, we're going to go down the columns and fill it in. So zebra here, which was our one-dimensional array, got put into a matrix, and it went down by columns, and I told it 2 columns, 5 rows. Okay. Often we want to control that, how it gets put into our matrix. So we can do by row, and we set that to be true. Now rather than going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, left to right across the rows. Then we can retrieve information from a matrix just like we would a vector, but we have to now provide 2 indexes. So for a normal vector, we provide 1. We pull out the third instance. Now, if I want to pull out the first row, first column, I have to say 1, first row, 1, first column, and I can retrieve that value. If I wanted to get the second column, I can get it that way, or second row, second column. I can get whole rows as vectors by just omitting after the comma or before the comma. So for a row, I just give it the row index I want. Here I want the second. For a column, I can just put it after the comma, and I'll get my second column. And again, with this, we can also do replacement. We can replace whole columns at a time or whole rows at a time using the same indexing and replacement rules we learned for vectors. Another nice feature is we can do vector arithmetic operations. So we can divide whole vectors by other vectors, and here I'm going to divide my column 1 by my column 2. So I'm going to take the index comma 1, comma 2, and then I get my vector of these values divided pairwise by the equivalent value in the other column. Okay. So once we've done matrices, we moved on to our last part from yesterday, which was a little bit more custom to R, I guess, and that is factors. So we know we can make, I don't know why I'm choosing animals now. We know we can make numeric vectors. We can also make character vectors. I don't know, now I have to think of sheep names. Dolly, Bar. So we have our sheep names here. We can do, if I did something a little bit clever, put Dolly in twice. We can do unique, which is a nice method we can apply to a character vector, and it will just give me the unique values in that vector. If we have multiple values in a vector, we might actually be dealing with categories. And if we have categories, a better thing to use is actually a factor. Okay, so a factor stores our information in a similar way to a vector. So we have Dolly, Bard, Tom, Dolly, but we also now have levels, okay, which show us the different groups, the different values in our factor. Okay, so there we've got Bard, Dolly, Tom. Okay, this makes factors a little more complex because if we want to replace values in factors, we can only replace values in a factor when we actually already have a value in the level. So if I try and put the first level and set this to be Bar or Tom, okay, but if I try and put a value there which isn't listed in these levels, such as Matt, it's going to give us this error, invalid factor level generated, NA generated, because it hasn't got any awareness of Matt in the levels. It gives us an error. Okay, so we can only ever include values here that we see in the levels. So those are our three basic types we've come across so far. We have our factor, we have our matrix, and now we have our character, our matrix, and our factor. Okay. An interesting point about both vectors and matrices, which is frustrating sometimes, is that these have to be one value. Okay. They all have to be numerical, they all have to be character, same for matrix, to the point that if we replace one value in this with a character, the whole matrix becomes character. So that's a problem. Sometimes we do want to have, a numeric value in this first column, maybe a factor in the second column, and a character value in the third column. So we need an object which allows us to do that. And there is obviously an underlying reason why matrices like to be one type of value data. It's because it allows us to handle them easier in R. But we do want another type of data, and that actually brings us on to our next section, which is data frames. Matrices, factors, and data frames. So data frames are fantastic useful object in R, and you can also find equivalent objects in Python and other languages. Fundamentally, what we know is that matrices, you can only have one type of data. So when we try to create, like I did just now, put in a character element into our numeric matrix, the whole matrix becomes numeric. And that'll be an issue if I want to start to do some arithmetic operations on my matrix. Even though maybe I haven't changed column 1, I changed a value in column 3, row 1 to be character. Now I can't do my sum of column 1. So in practice, we probably want tables which are a mixture of these data types. We want a table maybe with character for the gene name here, maybe a factor for the type of gene it is, and a numeric value for the score, the signal for that gene. So in R, we can make use of this data frame object, and this allows us to store tables with columns of different data types. So to create a data frame, we just need to use, rather than the matrix function, we're going to use a data.frame function. There is a slightly different way of setting it up. So we just need some different data types. First one, we're going to take our character vector. So I do combine, I give it my 3, 4 strings I want, my patient names, not very personable, but patient 1, 2, 3, 4. I'm then going to produce a factor. And to produce this factor, I'm just going to repeat. I'm going to take a vector of male, female. I'm going to put it to the repeat function rep. And I'm going to repeat male, female twice. And then I'm going to turn that into a factor. I'm going to call that patient type. And then survival, I've just got here numeric random survival times 1, 30, 2, 20. So now to create a data frame from this, we don't give it a vector and tell it number of rows, number of columns. We're going to tell it explicitly, this column here, I want a column called name. Put the patient name information in there. I've got a column called type. Put the type information there, survival time. And I want to put that numeric vector there. I don't need to tell it what type of data is going where. I don't need to say I'm putting a factor here. I can just tell it this is the column and this is the data I want to put there. As long as it's the same length as the other data types, it's not going to give you an error or a warning. And we get our first data frame and it looks just like a matrix, really. So these can be indexed just like matrices. We can use all the same rules. If I have my data frame here and I want to extract those with survival times greater than 10, I can do data frame, I'll index it, I do my comma, and then after the comma, because I'm going for columns rather than rows, I give it the index of the name of the column. So I'm telling it, take the survival time column and check the entire vector extracted to see which values are above 10 and use that, like we did with matrices, to index which rows I want to pull out from my data frame. And that will give us patient 2 and patient 4 both had significantly increased survival time. I just noticed this, the males really didn't do well here. I think that's by chance. Unlike matrices though, there are some really nice additional features to data frames we can take advantage of. And one of them is this dollar symbol. And we'll see this again with our next data type. And you'll see this a lot with objects. So as we get into more complex R. So if we want to pull out a particular column, we don't need to necessarily do this square brackets, comma, and then the name of the column. We can actually just do dollar and then give it the name of the column afterwards. Okay, so by putting dollar, it knows we're looking at columns, and then I just put survival time as the name of my column. And I get exactly the same as if I pulled it out from indexing it this way, like a matrix. And that can often be easier to write out for situations like this, where I just want to take the survival time column, find those here less than 10, it's just the males. Okay, but indexing this way is exactly the same as indexing this way. It's just a little easier, perhaps. So another nice thing about this dollar is actually in R, and it doesn't matter if it's R or RStudio, this is going to allow you to auto-complete your selection. So if you have, if we look at our data frame here, we have name, type, survival time. Okay, these are all very unique names. Actually, you don't need to type in the full name. So in R, you can actually just get away with doing enough after this dollar sign to make it unique. So serve could not possibly match any other columns. R is clever enough to go, okay, he means survival time. Here you can actually just get $S and it would know to pull out that survival time column. This works with the data frame way of indexing. Actually, it works with any type of dollar indexing, but it's not going to work with this standard indexing. So we can't put this quote and then put some shortened version of our column name. It's just not going to be able to work out what we're after. Okay. So this dollar operator has got another use other than just selecting. So, I want to select this column, or, the full name for this column. It also allows us to add new data. And if you remember with matrices, we always needed to create a vector which we would see bind on to our matrix. In this case, we don't need to do that anymore. So if I want to create a new column on the fly, I can just do my data frame dollar. I need the exact name of what I want to call my new column. Right, so in this case, rather boringly, I'm calling it new column. And then I just need data to go into my new column. In this case, I'm just going to repeat the character new data, and I'm going to repeat it the number of rows in the data frame. Okay, then I can be guaranteed it's going to be the same length as the data frame. N row pulls me out the number of rows of the data frame. Okay, so it's really nice. It's just much easier to work with data frames with mixed data types, but also these things like dollar to extract information, but also add new and add new columns. It's pretty useful. So we can do replacement in the same way as we've seen for the less complex data types. Again, we just need to use this assignment here. So in this case, I want to go into the survival time column, and anyone who survived less than 10, I'm just going to mark them as 0. Some type of thresholding. Anyone who was less than this, I'll just say 0. Okay. Nothing new here. This is exactly like we did for the original matrices. So it should work just the same. When we work with factors for replacement, so when we were trying to replace things like this type column, which we put in as a factor here, on patient type, it was a factor. And we put it into this type column here, type, patient type. When we start to work with this, we're going to have same issues as we had with other factors. Okay. So we're going to get this NA issue, and that's because in this case, I'm trying to get that first row from the type column. I want to replace it with other. That wasn't in the levels we originally had. I don't think I set levels, but there was only male and female in that factor originally. So I can't just replace it and put other there. It's going to give me an error and put NA there. So I need to do what I did with factors, but now inside this context of a data frame. So again, I'm going to create a new data frame because I just ruined it by putting NA there. So now I'm going to create a new data frame, but with the same information. And now I can just update that one column, and I'm going to update the levels in that column. So what factors can be available, or what factor names I can actually use. And I'm just going to do or combine the present levels in that factor, so I can extract them with levels, and I'm going to add to them because I'm combining to them other. Now, when I want to go replace it with other, it's not going to give me an error. It's just going to be able to put it straight in. Okay. So this is just the complexity of factors. We can't put anything into a factor which isn't in its levels. Levels are established when we build the factor. So often we need to do something like this. If we come across a new data type which we want to put in there, or a new category, we just have to reassign the levels. It happens in factors, and it happens in data frames too. Now, perhaps because of these reasons of NA replacement and this actually being a bit of a pain, this changed in R, or how we get data frames together, and how we assign categorical vectors to factors changed in R about version 4. Okay, so this is going to be more of a problem, or more of an effect later on when we're talking about reading in data from external files, so reading data from Excel or CSV or text files. And previously, the default was when you read in something from a file, or when you build a data frame yourself, it's going to set strings as factors. So anytime you have a character column, it was going to try and set it explicitly to be a factor. It believed that you wanted to work with categorical data. This, as you can imagine, would be a problem because lots of people would read in their data and they just want to replace little bits, and you would end up with this NA, which maybe isn't really expected. So sometime around R4, or exactly on R4, this got updated. So when we started this course, 3.6, 3 point something, it was different, and this was more of a problem. Now, actually, this data frame function, it has an argument strings as factors. By default, that is set to false. So you have to explicitly put in a factor into your data frame. Previously, and you could actually do this yourself now, if you set strings as factors to be true, it's automatically going to interpret all your character vectors as factors. And then anytime you try and replace a value in it, in this case, patient name, which we know is a character vector, go back to prove the point, that is a character vector. If I set strings as factors as true now, and if you're working in an R version previous to R4, I think we're on R4.1 now, then you'll get this type of error for any character column. So that used to be an issue, less of an issue now. You can make it an issue for yourself. Factors seem troublesome at this point, right? Because we have to replace, we have to do things like this levels command to replace them. The use of factors in data frames will become really clear when we start to do plotting, because it actually controls how you group your data. And when you really have categorical data in that column, this is really useful. It's going to make boxes based on the categories automatically. So there is a use in these factors in data frames. Okay, here just showing you that you can just set this to strings to be false, strings as factors as false, and then it doesn't matter. We can replace any of these columns then just as we would like, just as a normal character vector, but it's not a factor anymore. So these things like plotting we will come across later on, statistics with dseek and RNA-seq, they need these to be factors. So we'll have to still deal with factors as we go along. A really useful function in R, and especially when you're working with matrices or data frames, is order. So for numeric vectors, order by default returns the indices of a vector in that vector's increasing order. So this behavior can be kind of reversed by using this decreasing argument. Right, so there's this function here which really allows you to see what order a vector should be in if it was to be decreasing to increased or highest to lowest values. So here we're going to do test order, and I'm going to set 20, 10, 30. And then if I do, here it is, and if I do order, test order decreasing equals true, it's going to tell me the third one should have gone first, then the, third one should have gone first, then the first one should have been second, and then the second one should have been third. Okay, so these are the indexes in order to put them in order, right? And allow us to put them in order. So if I do test order, and then I just default order test order, because the default is decreasing equals false, it puts them automatically in decreasing order for me, increasing order for me. And here, if I do test order and I change my decreasing order argument to true, now I'm going to get them in decreasing order. When a vector contains NAs, and it really might, if we're starting to do these divisions, and it's just not possible to do the calculation on the values we have there, maybe 0 divided by, or something divided by 0. When a vector contains NA values, these NA values will by default be placed last in the ordering. Okay, so here, if I do 2, 1, and then I have an NA value, 3, so the NA being not available. If I then try and order this, and this is by default here, and I want it decreasing as true, and I've set NA last equals true, but this is the default for this argument. Then it's going to give me 3, right? That's the highest number, then 2, then 1, and it will place the NA at the end. If then I want to do control this, I can actually say decreasing equals true, but I can say NA last equals F, false, and it will put the NA at the beginning. This is really useful because sometimes you will have a long vector and you want to extract the last values, so the bottom, the lowest values. You would think naturally I'll just order it and take the last values in my, or maybe the last value. It may be that your last value will be an NA, right? Because NA last is true. So if you wanted to take the last value, you would do NA last equals false, and then you can be sure that the NA won't be at the end of your ordered list, ordered vector. So if we can order vectors, we can use the same trick to then order our data frames, which will be very useful to us. So here we have our data frame name, type, and survival time, which is clearly unordered. If I want to order that, I can just do what we were doing earlier on with vectors. So I'm going to do order, and I'm going to extract the vector for this column here, and I'm going to do that by doing data frame here $, and because I'm using the $, I don't need to use the full name. I can just do serve, and I'm telling it decreasing equals true, so it's going to go from highest to lowest, And then I'm giving that to the index for rows and before the column, comma. And now I have my ordered data frame. We could also arrange multiple columns, which would be very useful. You might want to, resolve within one column first and then sort in there. So we can do that by providing multiple vectors to the order argument, and we just need to separate them by comma. And at the end, we can still specify our decreasing equals true or false. So it's going to go and look in the order that you've provided them to the order function. It's going to take our first one here, and it's going to sort them by type, male, female. And then second is going to then sort them by survival time. And then here it's going to be 2, then 1, and then 30, then 20. Okay, so we can do nested sorting within groups in our data frames too. What am I doing for time? Really useful operation. I think this is special to data frames. Can't do this with matrices. Is to try and join two data frames by a column of common values. So you have half your patient information in one big table. You have more information on your patients, maybe addresses, contact information, another table. You want to join these together so that you have one big table to operate on. The only common column is patient name. So we want to join these two tables by, say, patient name. So in this case here, we have our original patient data frame. We have DF here. Create our data frame. Don't need to specify anything special. Just name is patient name, type is patient type, survival time is survival time. And then we have another data frame here. It doesn't need to be the same dimensions, so it doesn't need to be the same number of rows, doesn't need to be the same number of columns. But I have a column called name, so that matches across these two data frames. And then I have unique information, such as height here, which is just a numeric vector. So to join these two, we can just use this function merge. So merge is going to take two data frames, its first data frame and its second data frame here. And this is actually going to be the order that they appear in the columns when you have your joined merge data frame. So it takes your first data frame and your second data frame. So here's your first data frame. Here's the second data frame here. We tell it what column we want to merge by. And in this case, I'm giving it the index of the column I want to merge by, which is 1. And then I can tell it various combinations of how to keep the data. But here I'm going to say all equals false. And it's only going to keep data which is in common across both data frames. Okay, so it's not going to try and keep all the data from both data frames. It's actually going to be false, and it's just going to keep the data which is in common. Okay. We saw when we started this last time here, 1, 2, 3, 4. There was only 3 here, so it's going to throw away this patient 4 because there's no information in the second data frame on this. Okay, so we have some exercises here. I'm going to skip ahead just to the list section next, and we can come back and look at these exercises in this break. So the final type of data I'm going to deal with today is lists. Okay, so lists are the final type of data we're going to look at. So in our lists really provide a general container which hold any different data type, can be of unequal lengths, but you can still associate this into one object where you pull the information from. Okay. So if you have a data frame of information, and maybe you have a vector or a matrix, which you don't want to change into a data frame, but you want to associate these together, you could perhaps create a list and then just attach them all within this list object. So our first element is going to contain here, create a vector 1, 2, 3, 4. We're going to have a second element, which will be a matrix 1 to 10, n row 2, n col 5. So it's going to have 2 rows, 5 columns. We haven't set by row here. And then our third element will be our new data type we come across. It will be a data frame, and it's going to contain a numeric column and a character column. So we're allowed to do that in data frames, whereas in a matrices, we wouldn't be able to get away with this. So to create a list, we have a really simple tool we can use, and that is this list function. Right? To create a list, we just use list, and we just need to give it the elements that we want to put into this list. Okay, so here we have our first element, which will be our vector, our second element, which is our matrix, and our third element, which will be our data frame. Okay, and then once I've created it, it will look like this if I type this into our first element here, our second element here, and our third here. Okay, and you can see they're named in some way a little bit differently to what we've seen previously. So just like with vectors, we can also create these with names. So previously we did C, and we can actually assign names to them. Here we can do list, and I'm going to say first is first element, second is second element, third is third element. So if we look there, we have now our named list, first, second, third. Okay, and we can already see we no longer have this weird kind of double square brackets indexed. Now we have a dollar, and we have the name of our element there. So lists, as with other data types in R, can of course be indexed. We want to retrieve the information from them. In contrast to other data types though, we can't just use these square brackets to get at the information within a list. We actually need to look and produce these double square brackets indices in order to get the values within a list. So I'm going to show that here, but I'm also maybe just going to hop into R and show you that there as well. So in this case, we create our list, give it our first element, our second element, our third element. Now, if I was to do my standard index and do one square bracket and 1, you can see it still maintains this structure here where we have these double square brackets 1, and then we have the values in that element of the list still underneath. If I do the double square brackets when I try and retrieve it though, I actually just get the vector straight back. Okay. As with data frames, once we've named it, we can also get this value in the list, the actual element, the actual value within that element, by using the $sign and just give it the name, and I can extract it. So data frames aren't lists. We can use the same trick as data frames, and we can also use the don't have to write out the full name. We can just put here fir, and it will know to pull out the first. Just to show you something there, so let's hop out for a second into R. I just want to give that example. You can find this can be a little confusing with lists. So let's open our studio again. New session. So this is my 3 elements I'm going to put into my list, and they're all different lengths, different sizes. They're not different types. They're not going to be able to stitch them together in any sensible way while maintaining the data types. You know, this is a matrix. This is all numeric. So then we created a list. First. So that's my list. Like I say, if I want to, I can extract the values using my dollar thing. Does that work if I do this, actually? It does, so I don't need to use the full name. I could probably just get away with doing F, right? S. But if I do double square brackets, I also get the same result. So I can pull out the first element or the second element. But what's kind of frustrating to a lot of people is if I do this, I still pull out the list. So if I look at this, it's still a list, which can be useful in times, right? Because I actually get to maintain the name, But when I do a single bracket, I'm not getting the element, I'm not getting the actual data out of that element of the list. I'm actually just pulling out a list containing just that information. Okay, so there I get a list back with the information I want within the element still, but here I extract it from the list structure. Okay. Done that. So again, similar to vectors, we can actually join together lists into bigger lists. So here we have list first, third, second, third, the one we had previously. If I want to, then I can extract, I can add to this named list a new list containing just this vector 4, 4. Call it fourth, and I can just use my combine function, which I use with vectors, to combine my list into a longer list. Okay. Then here I can just, here I'm just extracting the first and the fourth element of my list, but still as a list because I'm not doing double square brackets, and I can see it's been added here. I think a lot of people will make this mistake, is that you can't just combine a list with a vector and hope that you'll get another list out. What you actually end up doing, if you want to say do C and you give it your present list, which was this my list or whatever, if we then try and add to it a vector of 4 and 4, actually it ends up putting each of these elements into their own list element, which isn't quite what I would have wanted here. I would have wanted to just attach that as a separate list element. So a really useful thing, which we'll come across maybe in the next few slides or in the for loops again, is that quite often you get values returned to you from a function or someone else's function as a list, and you want to flatten this into a different data structure. So you want to take this information from a list and put it into a matrix. Okay, so just to show you this in action, we're going to first create a list. I'm going to create a list where every element is the same length. Okay, so here we have first, second, third, and we can have the first element 1 to 3, seconds 2, 6, 7, third is 1, 4, 7. Now, once I have my list here, if I pass it to the unlist function, the unlist is just going to break out these elements and try and put them into one object. Here it's a factor, and you can see it's put my factor here, and it's gone off the edge because I've just taken the first 7. And it's done something kind of clever. It's added the name from the element to the name of my vector I just extracted. And it's also put the number after it to tell it what position it was in my vector here. Okay. So then a common thing, as I was saying, is that you will get results back from a list. Maybe you operate on every row and you get your results back as a list, and you want to flatten this and turn it into a matrix. Here we can just show this operation. We take the list, I unlist it, so I will produce this type of vector here. And then with that, I can do matrix, give it my flattened list. I can tell it to give me the same number of rows as were in my list originally. I know that they were all the same length, so I can tell it ncol equals 3. Importantly, I tell it to go by row, because I know that my values are coming in by row here, first, second, second. So fill out by row, and then I can also give it dim names here, which is just my dimension names. I can tell it to take on the names from my list. And then I can turn this list here into something like a matrix, and then I can start to do my matrix operations, column sums, row sums, divide one by the other. It makes my life a lot easier once we've got this into a matrix form. Familiar. Okay, so I think the last thing, oh, sorry, I have a question. I think it's just the order there, actually, to be honest. I saw that myself. I think it's just the order, but we can look in the gap at the end to assign that here. So in dim names, I think you can give it both But if you give it 1, it was just assigning it to the rows first and then perhaps the column second. But we can check that. I will do it at the end. So last thing I think with data types, and then we're going to talk a little bit in our next session about how we actually get data into R from external sources. Because often you will have your data as a matrix, and maybe you just want to turn this into a data frame for whatever reason, or you have a data frame and it happens to all be numeric values, and you now want to turn that into a matrix so that you can do some matrix stuff. There are mechanisms to allow us to do this in R, just transform from one data type to another. So if we want to know what data type our object is, and this really can be useful for when you're working with other people's tools, other people's libraries, it passes you back a result. You're not sure. Is it a data frame? Is it a matrix? Is it their special object type? You can always run class on any object returned to us, so any named variable, any of these things. If we run class on it, it will tell us what type of object it is. And then if we know that, we know what we can do with it. So here we're going to do class on my named matrix, and it's going to tell me it's a matrix. The nature of R, it's also what's called an array. If I do that on my data frame, it knows class, and it tells me it's a data frame. There are a set of functions, and there's another set of functions which are very similar, and we'll cover them a little bit later on, but they all start with as. So here we have our named matrix. If I want to turn this into a character vector, I can do as dot character, and then I just give it my named matrix. You can see it's extracting the values from this by column and turning this into a character vector. If I just said as dot vector, it's going to turn this into a numeric vector, which was actually what it was in the first place. If this was a character matrix, it would have turned it into a character vector. Really usefully are the as dot data frame, okay, because often we would want to turn our matrix into a data frame so that we can start to use these dollar things to add new values to it and perhaps add characters to this matrix, which we couldn't have done when we maintained it as a matrix. So as dot data frame, give it the matrix, it just comes as a data frame. Or we can do things like as dot list, which isn't so useful here, but in other cases can be very useful. So that's going to end the session here. We've got 10 minutes left, but we can give us 10 minutes break. When we come back, we're going to run through how we actually get data from outside of R. Clearly, you're not going to be typing in all your data. You're going to be reading it in from other sources like Excel files or simpler text files. But in the meantime, if you can run through these exercises here, it gets a little complex now, but we have our exercise on factors and data frames. So if you can run through that, and at the beginning of our next session, which should be at 3, I will quickly run through these solutions and address any questions anyone has as we run through them. So that's the end of the current session. I'm going to stop the recording, but I'm going to address your question, Calvin, as well. Just to answer your question, that's a good question. So, stop. Share. So I think it was, so Calvin had a question. Let me read it out because it was a nice question. And as I was doing this course, actually, I looked at this and I said, I wonder. So how does R know to assign dim names to the rows in the matrix as opposed to the columns? And I thought maybe it's just, if it's 1, it assumes rows. So we have here matrix, and we give it this vector at this point. We tell it the number of rows. We tell it the number of columns. We tell it do it by row. But then we say dim names, and we only give it the names of the matrix. Right? Sorry, names of the list. And the names of the list were first, second, third. And it put it in rows rather than columns. So why did it do that? So then I would go to matrix, do my question mark function. And I tell you, this is so useful. Underestimate, you don't need to go to Google a lot. So here we go, matrix data NA and row ncol and dim names equals null. So by default, dim names is null. Dim names attribute to the matrix. Null, or a list of length 2, giving the row and columns respectively. Okay, so we only gave 1. An empty list is treated as null, and a list of length 1 as row names. Great. So then I think that's what we've done here, right? Because we gave it a list of length 1, right? List, this is going to be length 1. Then it's treated them as row names. That makes sense, Kevin? Cool. It's great because, you know, I love these questions, which, you know, you can go to the help in there because it's a really great example of just how great our help is compared to other languages. Cool. So I'll be around. I'm going to turn off my screen, but I'm around. If you have any questions, hop on, let me know. Matt's here as well, so please ask him questions too. I had a comment on my AC. I'm sorry, it's boiling in here, so I have my AC on. I'm going to try and do something about that in a break. I'll speak to you guys soon. Bye. Perfect. So the first thing we need to do is with our new types of data, the factors, I'm going to create some of these. So create an ordinal factor. So it needs to have order containing height, named height containing high, low, mid, low, low, mid, high, whatever. So, you know, we can always start a new script here, file, new script. And then every time you see something with these commas, you can often do just a copy and replace to make your life a little easier. So let's do that. It's all, you know, that's going to just allow you, when someone is actually giving you strings of numbers or text to put in, you can often make your life a little easier that way. But actually skip ahead, and we're going to create, this would create our vector. It's all very good. But we actually want a factor, so we can turn our vector into a factor just by doing this. Maybe I should call that something different. Confuse things too much. And that would be pretty good, but it's not an ordered factor now, right? It's a nominal factor. We have levels, but we don't have that is greater than that. So I could do that just by saying ordered equals true, but then the order is not quite right? It doesn't have any knowledge internally in R that high is actually high. It just took the alphabetical order, HLM, and assumed that's what we wanted. So we can control the actual order going in with levels, and then we can just set our levels to be low, mid, high. So then we should have our ordered ordinal factor going low, mid, high. We did here. I'll copy and paste this so I have the same name. Okay, so that's the same. Great. Using a logical index, create a new factor of only those from height greater than low. Okay, so because this is an ordinal factor, we can actually use things like greater, less than, and it has an understanding that low, less than mid, is less than high. So here I think I'm saying greater than low. Okay, so the high is greater than low, low is not greater than low, mid is greater than low. And then we can just use this then to index now our original ordinal factor. So that's exactly what we did here. It's already seen it there, but filtered factor. It's easy. Replace the last index in height with very high. Create new factor with those greater than mid. Okay, so we need to do a few things here. First off, we need to refactor, re-level our factor. In this case, I'm actually just taking the original factor, ordinal factor, giving it back to the factor method. I'm telling it it's ordered, and I've just added into the levels very high, right, at the very end here. So once I've done that, I should be able to replace inside my factor with very high. We can see what happens actually if I did it without this. So now I have my new factor, and I can replace values in that. If I tried to take my ordinal factor and replace a value in it with very high, it's going to give me this error here, a warning to be fair, and it tells me an NA was generated, but I still got the value, my new factor back, but the warning told me what it did, it put in NA. Okay, we didn't want that. So we create a new factor from our previous one, and we're just adding an additional level. So next thing is we redid this trick we had before. If I want to get the last position in a vector or a factor or a data frame, last column, last rows, I can take the length of a vector, I can take the length of a factor. If it was a data frame, I could take the number of rows and row. If I wanted to get the last column, I could use ncol, give me the number of columns in place of length here. So in this case, I can just copy and paste that up there maybe. Actually, I save myself some time. They're not very easy to copy and paste from. So in this case, I get the length. That will be the same length as the factor, which was 10. That's right, is it? And then I can do, now I could just index that position, which is the last position, high, high. I'm going to change that to very high. I can do that because I've added here, very high. Once I've done that, I can just do the same trick I did before. Ooh, new factor. Oh, I'd already messed up my factor, my ordinal factor earlier on. I need to redo my ordinal factor because I already replaced a value in it. New factor, and then I can replace factor. Now we're cooking with gas. So that's just working on factors. The most important thing is how we can create new factors from previous ones. Here I did factor again. You could have used levels. And then here we had a little go with ordinal factors. Then I can create a data frame called annotation, okay, with column of gene names, gene 1, gene 2, gene 3, ensemble gene names, and pathway information, and gene lengths. Okay, so really we just need to put this information into a data frame. That's nothing too complex. Put it here. See the anatomy of this. And break this over multiple lines to make it a little easier for us to read. So we have our data frame function, right? This is going to allow us to produce the data frame. I then have my column name and then the data I want to put in that column. I have my other column name, data I want to put, pathway name, sorry, column name, pathway. Put all that, and it's going to create my data frame. Check the type of object by using this class we saw. Okay, so I have my data frame of annotation. And we just need to create a few more data frames here. So we have sample 1, sample 2. This is often what you'll see. You have one kind of metadata table. Maybe you'll read this in from Excel, and then you'll have results per sample. And here we have maybe expression for particular ensemble genes. So then we get to the more complex part of it, create a data frame containing only those gene names common to all data frames with all information from the annotation and the expression from sample 1 and sample 2. Okay, so annotation, sample. Okay, so we're going to use this merge function, and we're going to have to do this, and I think someone came across this in the exercises as well. Merge, this merge we're using, this function only takes two data frames and merges them. We can't put in 3 at a time. There are different functions and different libraries for things like this, but this is the most basic merge function in R. It takes 2 data frames, an annotation data frame, a sample data frame here, and we're going to merge them. And we'll start by merging 2, and then we'll have the result of that merge, and then we'll merge the third data frame in with that. So it's successively building up our bigger data frame. So first thing is we're going to merge these two samples. So we have annotation here, we have a sample here, and we're going to merge. We're going to set here that from the first data frame, by x equals 2. So that's going to be the second column here. And then here, by x equals 1. So my y, which is this, we're going to use the first column. And I say all equals false, so it's only going to keep rows where they're in common across both data frames. Next thing, we have annotation 1. So actually, let's run that and see what we get. Another sample. Okay. So now we can see we have the same information. Ensemble has now become the first column, and that's because that was the column we merged on. So it always becomes the first column, whatever we merge on. And then we have the gene names, pathway, and gene lengths from this data frame. And then we have the expression coming from this data frame. And we only have the genes, because I said all equals false. We only have the genes where the key, what we were joining by, were in common. What happens if we put all equals true there? I'm going to have to run this and thing. If we were to do all equals true, we can see that when it's actually missing a value, right? So this value, we didn't have an expression value for sample 1. What it's done is put in an NA for us here. So it's kept the rest of the information from the first table, the annotation, but for expression, it's put in our not available because it didn't have a value. Okay, but we don't want to do that. We want to do all equals false. We just want a nice complete table. So once we have that, our ensemble column is now the first column. So it's the same as it was in sample 1 or sample 2. Now we can merge in the remaining sample to this bigger table. And we'll get sample 1 and 2. We have all the information now from expression 1 or sample 1, sample 2. And we have the metadata from the original annotation data frame. Okay. So the other thing you could do here, which I don't show, but it's very useful, is, so here I've got two different columns, by.x equals 2 and by.y equals 1. My memory serves me right. We should actually be able to use the common gene name to merge these two. Sample 1. Okay. We don't need to, this is a bit more cumbersome. I need to know, okay, ensembles in my original annotation table, which is all the way up here. Ensemble was my second column. And sample, it was the first column. So in our exercise here, I've had to say it was the second column here, the first column there that I want to merge by. You could just put by and give a name of a column, and it's going to go look up the name of the column in both data frames, merge by that name. Okay, so add extra 2 columns containing the length normalized expression for sample 1 and sample 2. Okay, so it's easy to extract. Now we have our table. I can extract whole columns by using this feature, okay, this $. But notice here, because there's only a difference of .x, I can't use the shortcut, right? If I do this, it's going to give me null, because it could be either of these 2 columns. I have to put the whole thing there. And if I want to do our arithmetic operation, I could do x over the gene lengths here. So I'm going to do it over the gene lengths. Okay, and then I could do that for both of the sample expressions. But what's really nice about this is we did this very similar to this previously for the matrix, but we had to create a vector and then we had to C-bind it to the original matrix. Here, I can do our division, and in the same row, same line, I'm telling it I want to put $, and I'm going to put it in this sample 1 LME. Right, and it can add that column on the fly to my data. I think it's a really nice feature of data frames. Matrices, that would be a real pain. So I'm just going to, let's get this all complete. Identify the mean length normalized expression across sample 1 and sample 2 for the ons gene. Okay. Mean, so I'm going to create here row names. So I'm going to add some row names, and this is going to make my life a little easier for when I extract this information, because I can now use on6 by adding row names here. I can now index by those row names. Right? So it makes my life a little easier. I can start to just extract information for gene ons 003. So here I'm going to do the mean, and I'm going to extract for this gene and this column, so the run length normalized expression for sample 1. I can do the same for sample 2. I'm going to combine them into one vector, and then I can use the mean function to give me the mean of that whole vector. Sorry, it's really hard to select from this thing. Okay. For all genes, identify the log2 fold change in log length normalized expression from sample 1 to sample 2. So I guess it's sample 2 over sample 1. And again, we can just do our arithmetic operations here. This is actually kind of straightforward, where I just do log2 fold change on the sample 2 LNE column, which I've just created, minus, because we're in log space, log2 of the sample 1 LNE. I'll just get log2 fold change. I think in my example, I attached the names here. So I could do names. Log2 fold change equals example. Finally, I think this is finally, identify the total length of genes in the glycolysis pathway. Great. So then this is just a bit more complex subsetting. We have our glycolysis pathway. I can either do this, glycolysis, spell glycolysis, or I could use at the equals, or I could use our in operator, which we saw the other day. And then I can use that. I've now got the index for my rows. I want to use columns for this particular calculation. So I'll extract that. That's my index now, where I want to extract information in the data frame. Okay, so just to genes, or where the pathway was glycolysis, and I'm now extracting the gene length column, and I can get the sum of that. Okay, so that's the end of those exercises for data frames. It's getting more complex as we go along, so I really encourage you to continue following along these exercises. It will make your life easier if you follow along and do them all as well. This, as a lot of you probably noticed, we have exercises in here which are the same material really, but now applied to a different data type. So it's kind of building up over as we go along. This last example here actually identified total length of glycolysis pathway. This is one of the normalizations we need to apply when we're doing RNA-seq later on. Some pathways tend to be longer, have longer genes, and that can cause biases. Okay, so this is the exercises, and we're going to go on now. We did lists, did coercing data. Now we're going to go into the last session. Maybe we'll do a little bit of conditions, but this is the last session for our first set of exercises. First session. Okay, everything's recorded, shared. So most of the time, we're not going to be generating data in R. You're not going to be writing seq1 to whatever. You're going to be working or importing data from external files, and then getting these into R, operating on them, and actually you're going to be wanting to export to external files, because lots of people like to read your data in Excel. Like we said at the beginning, there's something about tables, rows versus columns, I think we find quite easy to interpret. So we like that type of format. So a lot of data is held in tables, and we want to export it back to something like Excel. We can give it to our PI, we can give it to our colleagues, we can give it to our collaborators to go review the data we produced in their kind of favorite Excel, OpenOffice, table reading software. Obviously, I'm going to talk about tables. I'm talking about data from external sources. I'm talking about tabular data here. We will move later on how you get data in from more complex data types specific to high throughput sequencing. But this is just focusing now on something which really has nothing to do with high throughput sequencing. It's generally useful getting data in to R. So this is what a table typically looks like. You'll have column titles, right? These is maybe your sample one expression. And you'll have maybe a column which actually gives you the row names, and maybe you'll have a title there as well to tell you this is gene names. So this is what we typically deal with when we're working to try and bring data into R. Tables from text files, so standard text files, can be read into R using things like read table. Okay, so read table, most simple function to read things, the most simple, but it's one which you can use daily. It's in base R to read data in. So here we have some data, and it's in our data directory. So this is where the working directory is going to come really important. We can read it in from there and get it into a data frame type format here. So let's just go look at what this data looks like actually I'm sharing my whole screen. And let's go look at actually what this looks like in a file. What did I say I was reading in? Read this table. Here we go. View file. So what does this look like? So this is like a really basic form of holding data. It's called comma separated values, and it's exactly what it says in the tin. Every column, every cell, going across the columns is separated by a comma. Okay, moving along. So this is our first column, second column, third column, fourth column, fifth column, sixth column, seventh column. That's comma separated values. You often get tab separated values, right, where we'll have a tab rather than a comma, or you can have just space separated values. A nice feature or an important thing which has happened here is that we have quotes around our values we're going to read in. Okay, and we're going to see that when we export and read in. And this is going to save us from a real pain, which ruins a lot of my sheets. So in this case, we have a gene name A. If it had a comma in the name, gene A comma, it has a comma in the name, or you've written a bit of text and you want it to be in your table and it has a comma in it. As you can imagine, if the table is using commas to separate your results, separate your columns, having a comma in the middle of your names can become a problem because it can see this and it will try and split it into a column. That doesn't happen though if we wrap everything in these quotes, right? It's clever enough that anything in a quote we don't try and split by. So this here, we have all our values in quotes, and we have commas between the values across every column. And this is the default simple way of storing data. You don't need a complex program to open this. And I think if I was to try and open this in, it's going to import it in R now. But if I was to try and open this in Excel, it would know CSV. I open this like a standard table. So to read these basic types of tables, we can use this read.table. It is inside our data directory. Sorry, I'm going to break out into R again. So this is if I go to my session set working directory, or maybe more go to working directory. So this is my working directory. Inside data, I have this file. Okay, so now I have to go data. That's the folder I'm going in, / and that's the file I want to read. This argument read table, it takes a few arguments, but we're just providing 2 here. This function read table takes a few arguments. We're just providing 2. And one is sep. This is the separator. So in our case, it's going to be comma. And then it knows comma separated values. So it will try and split this into columns for us based on the comma. If you wanted to do tab, which is TSV usually, you can't, well, you don't just leave a tab space there. We have a special character for tab in R and other programs, which is \T. If I needed to read in a tab separated file, I would put \T there. And then we have an important argument, header equals true. So this is telling it, expect the first row you read in to be the column names. Okay. You can imagine if you gave it a table with no column names, this could be a problem and you end up skipping off the first row of information because it's going to assign it to column names. So I can do read table, given my file, my path to my file, separator, header, and now I have my table for first four columns, first four rows, and then the first three columns. So read table allows for significant control, and there is something called scan, which is the very low level how to read a file in R, but it's very low level. It doesn't try and make matrices or rows from you, it just reads it in as one long string. So we use read table, and this allows for really nice significant control over how you're reading in the data. So it can do some things as you're reading in the data. So we can use our favorite thing in R, we can do question mark, read table, and we can go have a look at all these wonderful features. The first thing we can see is that there's a whole family of these read table kind of functions. And by default, read table, well, this is really what makes read table different from, say, read CSV and read delim, and that is defaults. Okay, they're pretty much the same program. They're going to do the same things, except read table is going to have sep as to be nothing. It has no knowledge of what separator it would be. Read CSV knows that it's going to be a comma. I guess read CSV2 believes it's going to be a semicolon. Read delim, it's going to try and automatically read a tab. So some people who always write in CSVs or delims, they will always use this. I like read.table. I actually use read delim a lot because I write a lot of tab, but read table is like the most simple version of this. We can already see this strings as factors thing there as well. So lots of information on the arguments, header, separator, quote we talked about briefly. So this is whether or not your values are quoted in order to protect from commas, and lots of information. We're going to start to play with a few of these to allow us to read in some more complex files now. Okay. So one of the really useful ones is row names. Okay, so you can actually specify as you read a table in, which column do I want to be the row names for my file. Okay, so here we're going to set row names to be 1. Right, so if we looked here, when we read it in, we had this gene name column. We actually saw it here as well. We don't want that to be necessarily part of our data frame. It will act as a nice way of indexing our data frame, maybe later on. So we can actually just specify here, row names equals 1. And when it reads it in now, this is automatically put into the row names. And then we have our matrix, sorry, our data frame just of numeric values. Yeah, well, I guess I'm not going to do it, but clearly you can now start to see the advantage. We talked about data frames all being multiple types of data, but matrices can only ever be one. If I wanted to then do a as.matrix on this, I need it to all be numeric. So by reading in with row names equals 1, saved me some time. It's put this character information in the row names, and now I could put this into a matrix and start to do numeric operations. This is really useful. As we get into gene expression data, this is something we do a lot. As mentioned, data which read into R through read table, it's going to be this data frame class. So it's going to read it in, and that makes sense because it's most often different types of data in different columns. So this is probably where people who worked in R before R4 saw this problem. We have this again, strings as factors argument, and I just alluded to it when we went to the help. So by default, this used to be true, which meant every time you read in a table, any character columns were treated as factors. So we had all this problem with replacement and becoming NAs, etc. So in this case, we can just set, well, it's automatically set for us now, but if you're in versions previous to 4, you can set strings as factors to be false. And when you read in this table, this column here will now be treated as a character vector rather than a factor. Sometimes you still want to read these things in as factors, and it will become apparent again in the plotting. So other very useful functions which read table has are skip. Right, so skip, set the number of rows to skip when reading, and comment char, which is really useful, which is going to set an identifier for lines not to be read. So if a line starts with a particular character, a $sign, usually a hash mark, it's just going to skip that line. It's not going to read it. Skip, we actually set the number of lines from the beginning of the file that we don't want to read. So I guess we got some exercises on that coming up. Okay. The read table function can also read data directly from HTTP, I think FTP, HTTPS. It doesn't need to be local on your computer. As long as you can get it from a publicly available website, you can download it. So FTP, HTTP, HTTPS. So we have some data here sitting underneath our website where we have all of these code, all these courses. I don't need to change anything in the read table command. I don't need to say read URL or anything. Just read.table. I can give it the URL, and I can do separator equals comma, header equals true. Probably should have done row names equals 1. But I can get my table. Okay, so it doesn't need to be local. This can be really nice if you have stable URLs you always want to read data from. Another nice feature about Windows versions of this, I think this works on Mac too. It's a slightly different command. Is that once you've copied and pasted something or copied something, so you can go into Excel, copy a big section of the table you want to read into R, and you can just go read.table file, and it knows that when you say clipboard, it should look inside your actual computer's clipboard, and it's going to read that and put that to table. Again, you still need to know what the separator was, what the header was when you do this. So read table by default will read every row and column of a file. Scan function, which is something I said at the beginning is like the lowest level reading function, allows for selection of particular columns to be read into R, and so can save memory when the files are large. If I have a 1,000 column matrix, 1,000,000 rows, and I only want one of those columns, there's no point me reading it all. So I can actually set what to read from my table using this scan function. I still give it the name of my, still give it the path to my file. I tell it the separator. I can tell it to skip particular rows, and here I'm asking it to skip 1, which will be the column headers. I just need to then say what type of information is within these columns, and here I'm telling it the first column is character, which makes sense, right? It's a gene name, and then I say numeric, and all the other columns are then going to be numeric. So these are the expression columns. We've only seen the first 3, but there are 6. Okay, so actually this, we're going to come back to scan later on. I think I just wanted to show it here. So when we get to things like BAM files, how we hold our high throughput sequencing, often we don't want to read the whole data. You may only be interested in the position that your reader lines in sequencing. You don't care about any other information. So a lot of programs will build on scan. I'm not going to go into it. Maybe we can have a quick look at the help. I'm sure that help for scan is probably fairly comprehensive. Yeah, it's a lot of help there. Okay. Once we have analyzed our data in R, and this is as important as reading in, right? We need to then get it back out to a file, hopefully a file we can open up in Excel it's formatted in a nice sensible way that we can open up in Excel, OpenOffice, LibreOffice, whatever your page is, whatever your favorite program is for this. Very easy in R. It's like the opposite of read table. We have a write.table. We just give it our table-like object. So this can be a data frame or a matrix. We tell it the file we want to write to, and now we can also say separator, and here I'm going to say comma. If we're using write.table, make sure you say separator. Otherwise, you're going to end up writing all your data to this table, which has no separators and no gaps between the columns. Remember, the default for write table was nothing. It was just space. Since our data has column names but no row names, that's true. Oh, it doesn't. Nope. Okay. Since our data has no column names but no row names, sorry, I was just checking that here. So I haven't imported the row names in the last version. We have our column names here. I will provide, so we're going to write them out, and we're going to provide additional arguments to our write.table. I'm going to say row names equals false, column names equals true. I'm just using T and F here. And then it's going to actually add the column names to the table when it's written out. If I put row names equals true, it will add the row names too on the left of the table. I'm going to make a little comment on this because this is, again, a really annoying thing about R. So let me try and get some data in here. So I'm sure we have an exercise on this, but just to make sure that we don't get caught by it ourselves in the future. So I'm going to build that table first. Let's get, maybe I can get it from here. That's our table. Let me change that a bit so I can do row names with 1. So this is the table in all its glory with all the values here. So then I just wanted to show you this issue with row names equals false. Okay, so if I write this out now, write.table, write.table, if I write this table out, file equals my table, set equals, comma. I have row names and I have column names. So I'll do row names equals false. Hold up names. Sorry, row dot names equals column names equals true. Row names equals true. Okay. So that's going to be create. Oh, I should have probably put CSV there. That will create a file in my current directory. There it is, my table.csv. New file. Well, the problem is, can I go to this directory, show folders in a new window? It'll take a while for OpenOffice. So, you know, this is importing into OpenOffice. As you open, I'm sure it's the same in Excel. I don't own Excel, but I can then say separator is comma. I will move my tab. Now I can just import this, right? But there is an issue, and this will affect anytime you write these tables out. Because we have row names, we actually have one more column name than we do, sorry, one less column name than we have columns. And that's because we've exported the row names. So every time you export a file with row names, you might have to find yourself doing this, right, which is a little bit painful. And there are solutions to this using things like tidyr. But just be aware when you write these files out, if you include row names, because the row names don't have a column title, when you import them, it's kind of stupid Excel and R. It will just read from left to right, find your commas, and it will put this shifted over by 1. Okay. There are ways to solve this. You actually just put the row names back onto your matrix or data frame before you export. But it's a common problem and it catches people out a bit. Okay. So in this case, row names equals false. We didn't have row names, so it wasn't even a problem. Column names equals true. We can write that in. It is important to know what your data is. So there are some nice shortcuts when you've read in a whole table to go and quickly review just the top or the end of the table. It's often there that you'll get some understanding. Okay, maybe the bottom of the table was broken, numbers are falling apart. So often you just want to check the top and the end. Head on your data frame is going to produce just, I think by default, head does the first 6 rows. Head, n, an integer of length up to dim. That's more complex than I wanted it to be. But I think we can specify how many rows we actually want to show. Head table, hopefully do n equals 2. It just gives me 2. Similar, I can do tail. I can do n equals 2, and it'll just show me the bottom 2. Great. So this is just a nice shortcut function, the equivalent of doing table and then indexing the first 3 rows or the last rows. But you can imagine it's actually a little trickier to index just like the last 4 rows. So just head and tail really allow you to do that easily. Oh, there we go. There's an example. Okay, so then a lot of the time working with CSVs is nice work. It's easy to do. We have write them out, we can format them correctly, we can read them in. They work well in R. Reality, though, is that a lot of data is passed around in Excel. Excel has some nice features of having multiple sheets. So like I was saying about lists, you can tie together results in a list, and it's easy to organize. In Excel, it's great to have different tables containing your information, and you can go through the tabs. You may get a massive set of Excel files, and you don't want to have to export the sheets separately to CSV in order to import into R. So we have a really great package, and it's called, deliberate gap here, I keep calling it RIO. It's RIO package. And it just allows you to do exactly what it says in the tin, read in from multiple different types of data formats into R. And it does it in a really nice, easy way that you're not going to have to learn too much more. And for me, I mean, XML's great. MATLAB, SAS, SPS, Minitab, if you're using any of these, you can import them into R from this. We're really for the Excel format. I think this is the most useful part of this package. I'm not sure, we haven't actually seen an installation of a package yet. So let's do this. Let's do our first installation. It should be installed on my computer. So let's have a look. So let's have a little look at packages. So there's another tab here on your right of your system called Packages. Maybe I've made this complex because I'm going to have a system library and RM library. But if you want to know you have a library installed, you can come here and go to your system library and you just type in RIO. I've already got RIO installed, a Swiss Army knife of data IO. Oh, I should have described it like that. If I want to load this library, I could either do my standard library, RIO, okay, or I can click and unclick here. Right, so I'll do that. If I need to install a new package, though, that's something different. We haven't shown how to do that yet. Now, there are multiple ways to do this in R. I think the easiest way is actually in the terminal, install.packages, and then we can just type in RIO. No, nothing else needs to be done. And this goes up, and it looks at it. It looks for it inside what is called CRAN. This is actually RStudio's hosted version of CRAN. But it knows to go look in this repository. It looks for anything called RIO. It gets a version which matches the kind of R you're in, the release of R you're in. So I'm in release 4 here, so it got that version. Gets all the dependencies and installs it on your computer. Very simple, and the most important thing is it gets all the dependencies. So I don't install this and then it tells me you need to go get this for it to work. Maybe RIO is a little different, but so the other way we can do this is tools, install package inside RStudio. And there you have some options like local, but I can just type in what I want, and you can see it has a nice search inside there, right? So it makes my life kind of easy. depending on what I want to search for. I would do Rio. I wouldn't mess around with where it's going to install it. Always install dependencies and just install. So we just did it with the install packages. You do package name just inside this. This is like a normal function, but it has to be in quotes. And then I think if you just do something which makes no sense, there is a package called POM package. It will go off and say, nope, that's not available, and then tell you that. So once we have a package installed on our system, and I just showed this now, in order to load that package and make the functions in it available to you, you need to run this library and then give it the package name. In this case, library, and then Rio. So we can install all these packages all we want, but until I either load it with library, and once I've done this, you know, all the functions available to me are available to me from Rio. This is a Rio function import. But if I was to detach it and I try that same thing, it hasn't found the function. The tools within that library just aren't available to us. Right? So we need to load it. And then it's giving me some. I think it wants to install some other packages as like not as dependencies, but it can do a lot of things. So if it wants to read OpenOffice, it wants you to install a different package for that. Yeah. Now it's loaded. Once I've got it loaded, either through library or clicking here, now I can start to make use of the package and all its tools. And this is really where R starts to win. People have so many, there are so many packages, there are so many tools built for R to allow you to do all this interactions with other data types, other programs, other software languages. So the two main functions in the Rio package are import and export functions. So we have this import function, and this will allow us to read in pretty much any file. It can recognize the extension. So in this case, we give it read our file, and we read a CSV file. It simply looks at the file, goes, okay, it's a CSV. And then when you do the import, it knows what separator to use. It can make a sensible guess on your column names. And if we wanted to, we can control where, you know, making row names here. Okay, much simpler than just using read to lim, but in this case, it's a simple file to read. Oh, I think we lost a slide here. Okay, so I might have to fill in a slide here. I think I've lost something off the edge. So the Rio package, and what makes it really great is that it will import from Excel files. So they have enough technology to actually allow us to read in this Excel file without having to change it, translate it into a CSV. So I think this is the missing slide. And you can see I did no other configuration, but I managed to get in my first sheet from my Excel. And I can read that in, and now it's just like as if I read it in from read CSV, right? Because I didn't have to bother changing my Excel into a CSV. By default, it was only going to retrieve the first sheet. So when I ran import, it looks in the Excel, it takes the first sheet as they are ordered in your kind of bottom tab across Excel. If I want to, I could actually say, look, I want to read the second sheet. So I can say which, and I can say which equals 2. Now I should have a table. Right, so now I have my metadata information, which is why Excel's great. I can have my sample expression values, metadata in the second Excel sheet. But like with merging, I could also put the actual name of the sheet if I know it. Oh, I don't have a sheet called metadata. Oh, capital metadata. Okay, that's useful. If we want to import every sheet in one go, we can actually just run a slightly different function, import list. And then if I do import list on my Excel sheet with my Excel file with multiple sheets, it's going to go whip through them all and then make a list. And each element in my list is going to be named by what we named the sheet. I wonder if I've actually got. open up our Excel sheet so we can actually see what it looks like. Desktop here, of course, data. Yeah, so we can see we have two tabs: expression scores, metadata, and this is what we've been reading in. So in this case, it just takes the names of those tabs and it's assigned them to the element names of the list. Right. Cool. Actually, I'm just going to show us this because it's kind of nice. So then we have our table, and I can do my dollar, and I could extract my expression scores that way, or my metadata that way. Okay. And I could do that just with one line of import list, give it my Excel. That's exactly what we showed. I just showed, but you can use dollar to get like the data frame way of extracting it, or you could do the double square brackets, like the list style way of extracting it, and put your name of the element you want to extract there. We can also export our data back to file using the export function. We just need to specify the name of the file we want to write to. So here, we're just going to write out our expression scores from that list. So I'm using a table, dollar expression scores. Here they are. Export, give it the expression scores table as a data frame. And now I'm telling it the format I want to write to by specifying here XLSX. So I think that's like the latest format of Excel. And then it's going to go right into the file, just that sheet into the Excel file. If we wanted to, though, we could actually take all our list. So you can imagine you could build lists of information and then write that out to Excel as separate sheets. So in this case, we already have our table list here. Right, so we have our list, and this contains the data frame from expression. This is the metadata. And then we can just do export. First I'm going to rename them. I mean, they already had names, but I guess it's just to prove that we are actually truly importing and exporting. And then I can export my new named list to the file xls.x. And then that will contain now, hopefully contain multiple files. Where's that? Right. This one. Should have done that with OpenOffice rather than Pages. Yeah, so now I've got expression and I got meta here. So it's really nice when you want to export all your data at one time into an Excel. We've reached the end of the session now. It's almost 4. We have some reading and writing exercises here. And this is kind of short, but I think it's actually kind of complex as well. I think it's not straightforward. So give yourself some time to go through it. Maybe it is straightforward. I'll come back at around maybe just before 5. I will run through the solutions for this. I'll also record the solutions if you don't want to hang around till 5. They're already up somewhere, the solutions on our YouTube channel. I'm a little behind with putting anything up yet, but in the week I'm going to try and catch up and get these first 2 sessions on. Great, so I'm going to leave you to work through this exercises here. I'll be back at just before 5 to run through, but if you want to head off, please have a go at the exercise before you do, but we can always pick up the run through either just by going to the answers on the next slide, or you can see the recording of it at a later time. Okay, so I'll speak to you all either at 5 or on Friday. Hey Abbas, I got your email. I haven't had a chance to reply, but I see that you've talked to Kristen, so I think you're all good. Let me know if you want to catch up anything. You can either email me. What you might have missed is we also have Matt in the room. So Matt's in my team and he's running the training outside of the graduate school. So if you want to reach out to him directly as well, catch up on anything, feel free to.